Welcome to The Explainer. Today, we're going to talk about a chemistry technique that works by getting rid of something you'd think is absolutely essential: water. Yep, you heard that right. It's a way to measure the unmeasurable, and to do it, you have to completely change the rules of the game.
So why on earth would you ever want to ditch water in a chemical reaction? I mean, it's the solvent, right? Well, to get why, we've got to look at the problem with water itself. Turns out, the universal solvent isn't so universal after all. It has a pretty big blind spot.
Look, water is a superstar in the chemistry world, no doubt about it. It's everywhere, it's cheap, and it dissolves tons of stuff. But, and this is a big but, for some chemicals, especially those really weak acids and bases, water actually makes things worse. It gets in the way.
Okay, this is where it gets really cool. Imagine a chemical reaction in water is like a big party. Your strong acids, they're the extroverts. They walk in, completely break apart, or dissociate, as chemists say, and everyone knows they're there. Super easy to spot and measure. But the weak acids? Oh, they're the total wallflowers. They just kind of hang back in the corner, barely breaking apart. Trying to get an accurate read on them is almost impossible.
And that is the core of the problem. See, when you do a titration, you're looking for a really sharp, clear signal, the endpoint that tells you, hey, the reaction's done. But with these shy, weak acids, that endpoint is just a blurry mess. It's like trying to hear a pin drop during a heavy metal concert. So what do?
Well, you don't change the substance itself. Nope. You change the entire environment. You kick water out and move the whole experiment into a world where water just doesn't exist.
And that's where non-aqueous titration comes in. This is the secret weapon for all those weak acids and bases that just get lost in the noise of water. By swapping out the solvent, you create a brand new playing field where you can finally get that clear, crisp measurement you need.
Now, the trick is picking the right solvent. Think of these non-aqueous solvents as specialized coaches. Each one has a totally different strategy for coaxing those shy chemical players out of their shells. First up, you've got your aprotic solvents. These guys are like the neutral referees. They don't take sides. They're just there to provide a quiet, non-reactive space so the acid and base can finally interact without any distractions. Then you've got the protophilic solvents. The name literally means proton-loving, and believe me, they are. These are the aggressive coaches. They're basic and they crave protons. They'll march right up to a weak acid and basically force it to give up its proton, making it react and show its true colors.
On the flip side, you have the protogenic solvents. These are the proton donors. They're acidic, and they've got protons to spare. So when they see a weak base, they push a proton onto it, which cranks up its reactivity.
And last but not least, we've got the versatile all-stars, amphiprotic solvents. These are the ultimate utility players. They can swing both ways, donating a proton if needed or accepting one. They just adapt to whatever the reaction calls for.
So, you might be wondering, how does this all work? What's the magic trick here? Well, it all comes down to this really cool idea called the leveling effect. And this is what completely changes the game.
Okay, let's jump back to our wallflower acid at the water party. Remember, in water, it just stays weak. It barely reacts. Its true acidic nature is totally hidden. But now, put that same weak acid into one of these leveling solvents, like a protophilic one. Suddenly, everything changes. The solvent is so persuasive that it forces the weak acid to give up its proton completely. Our shy wallflower is suddenly the center of attention, acting just like a strong acid.
And that's the whole point. The solvent isn't just a background setting anymore. It's an active participant. It literally increases the strength of the weak acid or base, leveling the playing field so you can finally measure it accurately.
This whole technique is a massive game changer. It's used everywhere from making medicines to the chemicals in dry cleaning. But, as with any really powerful technique, there are some pretty serious trade-offs.
The advantages are huge, right? It lets us accurately measure a whole class of chemicals that were basically invisible before. This is especially true for organic stuff that won't even dissolve in water in the first place. It gives us those super sharp endpoints we've been looking for.
But, and here's the big catch, this whole process is incredibly sensitive to its old enemy, water. Get this, you can't have more than 0.05% moisture. That is an insanely small amount. Even a tiny trace of water can completely wreck the whole experiment.
And yeah, the problems don't stop there. For one, these special solvents can be really expensive and they evaporate easily, which isn't great for the environment. On top of that, you have to be super careful in the lab. You need to control the temperature perfectly and even keep the CO2 from the air from getting into your reaction. It's a lot to manage.
You know what's really fascinating about all this is that it points to a much bigger idea, something that goes way beyond chemistry. Sometimes, the best way to solve a tough problem isn't to mess with the thing itself, but to completely change the environment around it. By getting rid of water, chemists found a whole new way to see things. It really makes you wonder, doesn't it? What other huge problems could we solve just by changing the environment?